So, hey everyone, my name is Rishabh. I'm from Rise Labs, and I'll be talking about a work which we recently did called heterogeneous ZK proof aggregation. And so let's start. So, a little bit context, I guess everyone over here is familiar with ZK proofs and how do they work and what do they basically try to do. So, I'll try to cover like what is proof aggregation, what is ZK recursion, what is ZK difference between the two, aggregation and the recursion part, and different types of aggregation schemes that are there, and what are the architecture that we took. Okay, and if time permits, then we can talk about why do we need ZK proof aggregations. So yeah, like what the fuck is ZK proof aggregation first of all? So like if we have a lot of right now, as you guys know, there are a lot of protocols that are coming with on building on ZK. So there are many proofs that are coming on EVM, and there's a major bottleneck over there because there is a gas cost involved for verifying the snarks proof. And what if we do basically like take the bunch of proofs and write a circuit to verify all of them together? So that at the end we have one single proof which proves the validity of all the proofs together. So you can have like as an example, you can take like you can have multiple validity proofs of let's say ZK sync, and then you can combine like most of the rollups do this also right now, that they combine most of the proofs, like Scroll does this, they compose most of the proofs that they have and post single proof at the end, like batching you can say. So this is called this is proof aggregation, and the recursion is basically something which enables aggregation, you can say. So what you have is so you have verifier and a prover, which you know in ZK, right? So the task of the prover is that you give the input to the prover, and then it spits out a proof that convinces the verifier that yeah, this is something which I have done of. You have to believe me, bro. So the verifier verifies that proof, and he's convinced that yeah, this is something which was run by the prover. Now the verifier also does this some job, right? It's a computation. It's inside some computer that's happening. It's not magically verifying it, right? So in case of you can say in Snarks, it's doing if we take the example of Block 16, then it's doing the pairing checks. In the case of Starks, it's doing the Fry verification, which is basically verifying the Morgan proofs over there. So there is some form of computation that's taking place. Okay, and that can be written inside a circuit if you need. So when you write the verification of the proof, basically any proof, Starks or Snarks or whatever you say, inside a circuit, then it basically means that you are verifying the proof inside a circuit. And if you do some computation, extra computation, so let's say you take an example of let's say a VM. A VM basically does multiple jobs, and every step you are trying to verify the last proof that you are getting and do the computation of the current step also. So what exactly is happening is earlier you were getting two proofs. So you were getting the proof of step one and you were getting step two proof separately. Okay. Now what's happening is you take step one, pass in the proof of step one to step two. Okay. And then verify the proof in the step two and do the computation of step two also. So at the end that you get is basically a final proof, right? So this is some form of recursion. So this is a recursion. Basically, you verify the proof also inside the computation. So there are a lot of, I'm not talking about it. Many fields need to be taken care of. That verification takes place in a different field and proving takes place in a different field. So you need to take care of those. But yeah, if we are talking about high level only. So that's a basically a high level recursion and versus aggregation, you can say. And recursion can overlap with the, aggregation, but in aggregation, you mainly use recursion as a tool. So you compose different proofs together. So let's say if you have a star proof and you want to convert it to, let's say you want to aggregate. Let's take an example. Okay, so let's take an example. You have an FF long proof. So FF long is a proving scheme which is used by Polygon ZK EVM for verifying their state validity proofs on the EVM. So I'll talk about proving scheme, the whole architecture after 2 3 slides. But just for an example, assume that we have an FF long proof and you want to compose it with a different proof, let's say Halo 2 proof or a Starkware proof. So what you do is you want both of them in the same proving scheme. Then then you can basically easily aggregate them. So you recursively compose them. So basically you convert the Starkware proof into a common proof, let's say Groth 16, and then you convert the the FF long group into a common group, let's say gross 16 again, and then you combine both of them together. So snark aggregation is also something which I'll talk about. So you can combine those snarks together and produce a final snark then that you can verify. Okay. So I mean that's a simple example that I just took about. So aggregation is of different types, like ZK systems are of different type, like snark-based aggregation is there, stack-based aggregation is there, and there are folding schemes. So let's briefly cover them. Snark-based aggregation, you might have heard of. Gross16 is a popular example. FFlong, which I just told you about, it does some optimizations. It's a popular example which is used by ZK EVM, as I told you. So these are all snarks, examples of snarks. And for aggregation schemes, what you have is basically you have pairing checks. So pairings, you can imagine that you have some elliptical curve points. You can, if you don't know elliptical curve points, just imagine that these are some mathematical numbers that you have, and you want. So multiplication in elliptical curves is very hard. First of all, you cannot do it easily. So you know you need elliptical curve pairings, bilinear pairings to multiply two elliptical curve points, and there is a lot of maths that's going on inside. It's like Wheeler loop you need to use, final exponentiation, a lot of things. But you just understand that you have a pairing equation, and let's say you have 5 pairing equations for 5 different snarks. So what you can do is you basically aggregate, trying to create a random linear combination of those pairings. So SnarkPack, which is a famous aggregation schemes of Groth16, which I think Protocol Labs uses for IPFS, and it aggregates Groth16 proofs using this scheme only. You create a random linear combination of the different pairing groups that you have, and then you finally verify one single pairing that you have. So it means that you are verifying the final proof. Stack-based recursion. Stack-based recursion is very cheap, you can say, because most of the computation, the heavy computation that Ethereum does inside the pre-compile. So right now, if you verify a ZK proof inside Ethereum, it's basically that you're using a pre-compile. It's not very easy to verify the proof inside. There was a pre-compile 7, which reduces the cost a lot. Okay, so it's like 300K for gas for verifying a Groth16 proof. But under the hood, a lot of computation is done inside the pre-compile. So that's what makes the verification difficult, and that's the bilinear pairing check that needs to be done inside the pre-compile. Starks don't have that. Starks basically mostly use FRI schemes, Fry schemes. So Fry is basically like converting into Merkle trees and then committing those Merkle trees to the verifier. And then you verify the Merkle inclusion proofs for verifying the proofs. Okay. So there are a bunch of, so you have, let's say, everyone knows that in ZK proofs, you work with polynomials, right? So what you do is you take the coefficients of the polynomial, you create a Merkle tree out of those, and then you commit that Merkle proof. So Starks use that, and for Fry aggregation, you take a bunch of Fry, basically a bunch of equations that are there, which are coming out of your program. So if you have a VM, that VM trace is finally converted into a polynomial, and that polynomial is basically, you can say, combining different polynomials together and then taking the Fry scheme on the polynomial at the last. So that's what Fry does, and it's easy to compose Starks than Snarks. And then there are folding schemes. So folding schemes are relatively new, and not relatively, but yeah, they came out in 2021 with Nova. And what it does is basically you have an IDC incrementally verifiable based computation. So what you do is every step you verify something, you do the computation, which I told you the scheme that I earlier told you about. Yeah, you do some computation, you do the verification, and then you move forward. So the proof basically moves forward. And folding schemes allow you to do some, pre-computation. So folding schemes do not play an active role in the proving part. You use a prover which is normally used. This is mainly for folding schemes like a pre-computation, you can say, for the snarks, basically. Sorry. Sorry, we were here. So this is basically, you can say, used by RISC-0. I've taken the slide from there. And this is their high-level overview of how they use Starks, snarks, and compose them to everything together. So this is basically, like you can say, the VM trace that RISC-0 generates. So this is everything that when you write a program in RISC-0 or SP1, the VM basically generates a trace. And this is like running the computation and some numbers are getting generated. So what you do is you basically take numbers and you have constraints over here, you have variables over here, you have copy constraints, everything is there. You generate a polynomial and you generate polynomials for all of them, and then you try to come into that polynomial. You basically try to prove that polynomial to the verifier. So you take the verifier, you take the prover, and then this receipt is basically the proof, and then you try to recursively compose the proofs together. So this zero has that functionality called composition, proof composition. So it provides you inherently proof composition, so you don't need to worry about every 1 million cycle, it composes the proofs together. So you can take those proofs, recursively combine them, and get the final proof. So, but all these proofs are Stackr proofs. So because composition, as I told you, is easier in Stackr proofs. So all these are Stackr proofs, but you cannot verify the Stacks on the on chain, right? Because the Stacks are having a bunch of Merkle proof inclusion proofs, and you cannot verify them on chain. The size with law, gas limit doesn't allow it. So what you do is you recursively compose it to a groth 16 proof, which itself takes a lot of time, like the double of computation what you did just over here. So you convert that to a groth 16 proof, and then you verify the groth 16 proof on chain, because that's verified on chain. So you do that computation just for on chain computation. If you don't want to do that, you can stop here. Also, it works. So this is an end-to-end chain of how aggregation and recursion comes into play. And why am I talking about this? Because we also worked for validity proofs. We try to build an aggregation scheme where you can use bunch of validity proofs from different rollups like Starkware, ZK Sync, and Polygon ZK EVM. You can compose them together and try to get one proof, which you can post it anywhere. Like you must have heard of Aggregation, Awaits Nexus, and most of the chains are right now, like ZK Sync is building ZK Stack, and most of them are building their own stacks, right? So at the end, what will they do is basically take all the rollups, take their proofs, combine them, aggregate them, and just have a single proof of all the rollup state change that's taking place. So that's the design that we are taking. It's not very hard to understand. It's readable, right? Or should I do? I don't think it's getting. Cool. I'll just post the slides so that you can take a look. Or we also have an article you can take a look after that. I'll share the link. So yeah, we take the proofs, we fetch them from the rollup itself, and you can basically have a converter over there. So these converters are designed in ZK VMs right now, because ZK VMs abstract away most of the things right now. You don't need to deal with the complexities of writing a circuit. We did that with the, verifying the FF long proof. It takes a lot of engineering efforts, and it takes a lot of engineering efforts to see that the circuit is correct. You first of all write the circuit very long time, and then you need to hire people to make sure that every constraint, the soundness and the completeness guarantees are there for the circuit. So that's why most of the people are writing circuits in Cairo and all these ZKVM, so that auditing is also very easy in these circuits. So you take the converter in those ZKVM, you convert those proofs into a star, and then if you want, you can compose them together into a final snark proof that you can get verified, as I told you earlier, which RISC-0 is internally using. So yeah, you can find more information over here. The repo is public, and you can see the code. We also wrote an article for it. Yeah, framework for heterogeneous. So here I have explained in detail whatever you want to do. So I think that's it for me. If you have any questions, I can answer them.
So in this case, we are composing n proofs together into five. Yeah. Now, can I verify that one of the proofs which I had in there? Can I verify that?
Yeah, that's the completeness guarantee that you need to have. You need to provide a proof that this is something which was included in that proof. You need to have.
How do I identify the particular proof?
So that proof is posted in a DA layer, and you prove that that DA layer contains that proof, and you prove that this proof is containing that proof. Yeah.
Follow up on this.
Yeah.
I think it's similar to like how block aggregation works.
Sorry?
Job aggregation, job.
I'm not getting that. What is?
Any question, folks? Just give them a Telegram or Twitter later
Yeah, sure.
session so that people can reach out to you.
It's very small, but it's Rishotix everywhere. Telegram, Twitter, Gmail ID also.